published work in PRD. So in this work, we present a calculation to answer the question, which is the title of my talk today, that why is chemical freeze out at the chiral crossover temperature? So in the next few slides, I will first discuss what do I mean by this question, and after that, I will present our calculations and show some results to answer this question. So in this title, there are two temperatures mentioned. One is the chiral crossover temperature, and the other is temperature at chemical freeze out. So let me start uh, briefly discussing each one by one. So first, the chiral crossover. So as we know that normal nuclear matter under extreme conditions of temperature and densities, it forms a deconfined state of quarks and gluons. The phase is popularly known as quark-gluon plasma, or QGP in short. Now, lattice computations suggest that this transition from QGP to hadrons is a smooth crossover at zero baryon chemical potential. Now, QGP is characterized by approximate chiral symmetry, and as the phase changes to hadrons, this symmetry is spontaneously broken. And the temperature at which this happens is termed as chiral crossover temperature, and lattice QCD gives a value of about 155 MeV for this temperature at baryon chemical potential 0. Now, next, for the chemical freeze out, so the quark-gluon plasma is formed in the laboratory when heavy nuclei are collided at relativistic energies. The QGP so formed is only in local equilibrium. Such a fireball of quarks and gluons, the properties of such a fireball of quarks and gluons are inferred by studying the number and momentum distribution of hadrons that are emitted from this fireball. Now, as the fireball expands due to internal pressure, the temperature decreases, and as it cools below the chiral crossover temperature, it converts to hadrons, and the typical time scale for such an evolution is about 10 to 20 Fermi. The hadrons so formed may further interact among themselves, thereby changing the yields and momentum distribution of individual species. Let tau denotes the typical time scale over which yields change. So for a system which is not in chemical equilibrium, tau is a measure of the time which the system takes to relax back to equilibrium. And depending on its values, we have two scenarios. So if the relaxation time is less than the expansion time, then the chemical equilibrium will be maintained throughout its evolution. However, if the relaxation time is greater than the expansion time, then system will not be able to maintain its chemical equilibrium. And after this, yields do not change significantly. Now, this point where the yields are essentially fixed is called chemical freeze out, and the temperature and chemical potential at which this happens are called chemical freeze out temperatures and chemical potential, respectively denoted by TCFO and UBCFO. So the next question is, how do we determine these parameters? So people have used hadron resonance gas model to extract the freeze out parameters. So let me briefly explain the scheme. So the model consists of non-interacting gas of hadrons and resonances, and since the components are non-interacting, the grand partition function can simply be written as sum of individual partition function. And the number of ith particle can be obtained by taking the derivative of this partition function with respect to chemical potential. Now, this chemical potential is a linear sum of different chemical potentials weighted by appropriate quantum numbers. So, mu b is baryon chemical potential, mu s is strangeness chemical potential, mu q is electric charge chemical potential, and bi, si, qi respectively denote baryon numbers, strangeness, and charge of the ith particle. And it turns out that the number is given by this integration. Now in the laboratory, the colliding nuclei do not carry strangeness, so we can put mu s to 0. Further, fixing the colliding system of nuclei, it fixes the baryon to charge ratio. So mu q and mu b are not independent in that case, and mu q can be expressed in terms of mu b. So finally, we are left with two parameters: the baryon chemical potential and temperature. So for a particular experiment, one can perform a two-parameter fitting to the mean hadronic yields, and it has been observed that the fitting is fairly nice, and the best fit parameters give the values of TCFO and UBCFO. Now, this splitting can be performed for different experiments, and by an experiment, I mean choosing a different colliding energy and colliding system. So with this, I come to the question, which was the title of the talk. So here, the freezeout parameters from different experiments have been compiled in team UV plane, and each point in this plane corresponds to one experiment. So, for example, this blue triangle here corresponds to lead-lead collisions at LHC, and this black circle corresponds to gold-gold collisions at SIS energies. Now, different point styles correspond to freeze-out parameters extracted by different groups. So, for example, this red squares correspond to the parameters extracted by hadronic et al. And this blue triangles is the extracted parameters by Beccatinian group. Now, this pink diamonds here, it correspond to the parameters extracted from lead-lead collisions at SPS energy. And this black stars correspond to parameters extracted from gold-gold collisions at RIC. And it can be seen that the black stars and this this pink diamonds, they overlap, and the overlap mean that irrespective of the colliding systems, if the colliding energy is same, then the matter which is formed in such collisions, they freeze out at a similar temperature, at a similar parameters of temperature and chemical potential. So in the meantime, this gray band uh, is the result for QCD phase boundary from lattice QCD. And as can be seen, uh, that the two predictions, that is the chemical freeze-out parameters from HRG model and the phase boundary from lattice QCD, are numerically equal within this range. However, these two are entirely different scenarios. Lattice QCD discusses the equilibrium properties of the system, whereas chemical freeze-out is a result of non-equilibrium dynamics within the system. But still, these two temperatures are numerically equal. So the question is, whether the two temperatures being equal, is this just a coincidence or is there a physical explanation for this? And as I will discuss in the rest of my talk, that there is a physical explanation to this, and that is related to chiral symmetry breaking.
Just one quick question, Sushant. So Rajiv is asking that what's the width of the lattice band in MEV? Isn't it smaller in recent results? So if you have a quick answer, you can give it.
I mean, this is, I mean, you're asking about the width of the crossover?
Width of the lattice band in MEV.
I am not very sure about that. So I took this from this article, so I'm not very sure about that number.
Okay, so we can come back to it later. Okay. Okay, go ahead.
Okay, so having stated the problem, let me briefly summarize how to proceed in answering this question. So we have hadron yields. We have chemical freeze-out parameters from the hadron yields. Now, to show that the crossover temperature is equal to the freeze-out temperature, we need to show two things. First, that the chemical relaxation time in the chiral symmetric phase is small. This has been done in literature, and the typical time scale turns out to be 1 to 2.5 Fermis. The next thing which we need to show is that the chemical relaxation time in the chiral broken phase, that is in the hadronic phase, is large. Now, since the first thing has been done in literature, so to understand phase out, we concentrate on the chiral broken phase, that is in the hadronic phase, and calculate the relaxation time of a hadron gas, which is not very far from equilibrium. So for this, we first need to set up a transport theory for hadronic yields. But before that, we need to decide which hadrons should be included. So being the lightest, pions must be included. And for consideration of strangeness, kaons should be included. Then the SU3 flavor structure would force us to include the eta. And this gives us the full octet of pseudoscalar mesons. So these are 3, 4, and 1, so total 8. Now for zero baryon chemical potential, the proton number at TCO, the proton number is 2 order less compared to pions, and hence we can neglect baryons and higher mass hadrons. So this slide is the setup of solution, and let me now discuss each step in more detail. So the first step is to set up a transport theory of hadrons. So relaxation time has to be independent of frame choice. So we choose to work in a frame where the fluid is at rest. Now the system of hadrons, which is formed in heavy ion collisions after the transition, is dilute. This has been discussed in literature, and one such reference is given here. And hence the use of classical Boltzmann equation is justified. Also, since the system is dilute, only 2 to 2 reactions will be of importance. And in order to understand freeze out, it is sufficient to calculate the yields close to equilibrium. So the use of linear approximation is justified. So for ith species, we write the densities to be a perturbation from equilibrium densities. And in the
Just one second.
sorry.
Go ahead. I think we missed the last part, but continue.
Okay, so in the momentum integrated Boltzmann equation, if I do this and what I was saying, so I'll just repeat this again. So so we use a linear approximation where we write the densities as an equilibrium part and a small perturbation from this equilibrium part. And when we then in the momentum integrated Boltzmann equation, we keep this we put this expression and kept expand around equilibrium and kept terms which is linear in delta and I. So after some steps of algebra, it turns out that the equation which determines the approach towards equilibrium is given by this equation. So delta Ni, this for say eighth particle, the rate equation is given by this differential equation. Delta N is the perturbation. This angular brackets denotes averaging over thermal distribution. The sum is over the sum. This sum is over the reactions where A is in the initial state, and this sum over R bar is the is over the reactions where A is in the final state. So now since we have 8 particles, so this A goes from 1 to 8, so we have 8 such equations. However, we will now take advantage of symmetries and conservation laws to further simplify the problem. And the first simplification comes from isospin symmetry. Now, since the mass difference between isospin partners is less than the crossover temperature, we can safely ignore such mass differences and treat pi plus pi 0 pi minus to be identical, and let us call that pi. And similarly, we do that for k plus k0 and k bar 0 k minus. So now instead of 8, we have only 4 independent densities, and that will be delta n pi, delta n k, delta n k bar, and delta n eta. Now further, we have two conserved quantities. So net strangeness is conserved, and we have an accidental conservation, and this arises due to our consideration of two to two going of two to two going to so this arises because of our consideration of 2 to 2 reactions. So even if the inelastic reactions are taking place, the total number n, which is n pi plus nk, nk bar, and eta, that will be conserved. So now we had 4 densities and 2 conserved quantities. So we can eliminate 2 in favor of others. So we choose pi and we choose to take delta n pi and delta n eta as independent. So we write delta n pi as h pi and delta n eta as h eta. So the strangeness conservation will say that delta nk is equals to delta nk bar, and then the number conservation will lead us to will make these to take values minus h pi plus h eta by 2. So now we have 2 independent densities, hence 2 rate equations, and these rate equations can be written in a matrix form like this. So the information of cross sections of all the reactions within the system will be contained in this C matrix. And further, the elements of the C matrix have dimension time inverse. So the eigenvalues of this matrix will then give the relaxation time of the system. So the next input which we need to calculate and which we need for the calculation of relaxation time is the cross section, and we calculate cross sections with the help of parallel perturbation theory. So the octet of pseudoscalar mesons, they form the Goldstone bosons of chiral symmetry breaking of QCD, and chiral symmetry constrains the interactions among the pseudoscalar mesons. For example, at the leading order, the Lagrangian, which is consistent with chiral symmetry, is given by this, where F0 is the pion decay constant in the chiral limit, and M0 correspond to tree level masses. Phi U is parameterized in terms of phi, and this phi is a SU3 matrix which contains the 8 meson fields. At next to leading order, there will be 8 allowed terms in the Lagrangian. Each such term will be multiplied by a constant coefficient called as low energy constants. So the amplitudes from the calculation of amplitudes from such a Lagrangian has been done in this reference. We use these amplitudes to calculate the cross sections. Further, we enforce unitarity using a method called inverse amplitude method. And just to mention that at every mass threshold, the dimension of S matrix increases by 1, and hence there will be discontinuities in the amplitudes at every mass threshold. So we now have cross sections. So we can calculate relaxation time by finding the eigenvalues of the C matrix. But before presenting the results, let me summarize some important features of our calculations. So there are 12 input parameters in the calculation, 3 masses, 1 decay constant, and 8 low energy constants. But the masses and decay constant are known precisely. So the uncertainties in our results come only from the uncertainties in low energy constants. Further, after unitarization, the amplitudes will contain poles corresponding to resonances, and hence dynamical generation of resonances is an important feature of this calculation. And this can be seen in these two plots where I show phase shifts in the rho channel and in the K star channel. It can be seen in the rho channel, the phase shifts become 90° at root S around 770 MeV, which is the mass of rho meson. And in the K star channel, this becomes 90° at around 890 MeV, which is the mass of K star meson. And similarly, the amplitudes generate all the scalar and vector resonances till 1.2 GeV. And as a result, we do not need to include resonances as explicit degrees of freedom. Further, we do not need any ultraviolet cutoff as the amplitudes are unitarized. So now coming to the results. So this plot here shows the relaxation time, which is the inverse of eigenvalue, and plotted as a function of temperature. So there are 2 eigenvalues. The uh, the smaller eigenvalue is the slow mode, and the larger eigenvalue is the fast mode. And as the plot shows, the slow mode relaxation time is about 100 Fermi at a temperature 155 MeV, and this grows to about 1000 Fermi at a temperature of 100 MeV. Similarly, for the fast mode relaxation time, it is about 10 Fermi at a temperature 155 at a temperature of 155 MeV, and this grows to about 100 Fermi at a temperature 100 MeV. Now the system dynamics will be governed by slow dynamics, and as can be seen that the relaxation time near the crossover temperature is about 100 Fermi. And recalling that the typical lifetime of the fireball produced in relativistic collisions is about 20 Fermi, what this suggests is that, what this result tells is that the gas of pseudoscalar mesons, it cannot equilibrate chemically within the lifetime of a fireball. So next, here I show the angle which the 2 eigenvectors make with the pion direction. So the slow mode, it makes an angle of about 10 degrees, and it's almost constant. It makes an angle of about 10 degrees with the pion direction. And the fast mode, it makes an angle of about 60 degrees with the pion direction. So this means that the slow mode is aligned more towards pion, and hence the slow mode is dominantly pions, and fast mode is aligned more towards eta, and this means the fast mode is dominantly etas. Now, this slide here shows how our results differ from earlier studies along this direction. So this paper, they use certain parameterizations for hadronic interactions. Now, first column is the result, is their result when they include only pi, rho, and nucleons. And the second column is the result when they include other hadronic states like delta and omega. So as can be seen at lower temperatures, the results for their relaxation time is of the same order as our results. However, at higher temperatures, the relaxation time is underestimated. And similarly with this paper, so they use cross sections from chiral Lagrangian. However, they do not unitarize the cross sections. So this solid line is the thermal relaxation time. This solid line is the total chemical relaxation time, and these dashed curves are contributions of of individual inelastic reactions to the chemical relaxation line. So we need to compare our results with this solid line, and again we can see that at lower temperatures, their results for relaxation time is of the same order as our results, but again at higher temperatures, the result is underestimated. Now, underestimation of relaxation time at high temperatures, it occurs because they use unphysical inputs in form of non-unitarized cross sections. Due to non-unitarization, the cross section will grow to large values at large energies, and this will lead to such underestimation. And it is important to emphasize that our results seem consistent with Goldstone physics. Now, Goldstone bosons are non-interacting. This means that if the chiral symmetry were exact, then the Goldstone bosons of chiral symmetry, which is the octet of pi k eta, they should not be interacting. However, chiral symmetry is not exact. It is approximate due to finite but small quark masses. And as a result, the interaction among the octet of pseudoscalar mesons is proportional to masses. Now, in our our results show that pion is the slowest mode and eta is the fastest mode. And this is the first indication of Goldstone behavior because pion is lighter and eta is heavier. Now, the best check should be to vary the masses and see whether in the limit uh, mass going to zero, we get relaxation time to be infinity. Unfortunately, we cannot perform this check because the low energy constants are fixed. However, we can perform another check and which would be consistent with Goldstone physics, and that will be to remove eta from the system. Now, being heavier, if we remove eta from the system, the net cross section should decrease, and this should increase the relaxation time. We have checked this. This we have checked, and the results are consistent with this, consistent with Goldstone physics. Now, for a hadron gas, one would expect a typical time scale of around 1 Fermi, but our results for relaxation times are 2 to 3 orders larger. So we use dimensional analysis to understand this large values of relaxation time. So the dimensional quantities that we have is the relaxation time, number density, mass, and decay constant. So with the help of these quantities, we construct a dimensionless ratio like this. Now for slow mode, m is pion mass and tau is the slow mode relaxation time, and we find that pi is of that this ratio is of order unity, and it changes only from 1 to 2 as the temperature changes from 100 to 150 MeV. Uh, Now, this result that pi is of order unity is not possible with the values of towers, with the values of relaxation time from previous studies. And this discussion then suggests that long relaxation time is natural for a theory with octet of pseudoscalar mesons. Further, since pi is of order unity, I can bring tau to the left-hand side and I can write 1 by tau s as equal to sigma times number density, where this sigma is this, this quantity, the numerical value being 25 millibarn, and this is nothing but the total pi cross section at low energy. And surprisingly, this result that 1 by tau equals to sigma times number density is what one would get using kinetic theory arguments. Now, this simple result can only be obtained when the complexity of next to leading order chiral perturbation theory and Meson resonances are included. And as a further check for fast mode, mass will be eta mass, and tau will be the fast mode relaxation time. And again, we see that pi, the ratio is of order unity, and it changes from 2/3 to 4/3 in the temperature range 100 to 150 MeV. And this means that the value of relaxation time for the fast mode is again natural. So coming back to the main question, that whether the chemical freeze out temperature and the crossover temperature are equal. So as I discussed, that the slow mode relaxation time is 100 Fermi near the crossover temperature, and which is much larger than the expansion times, which is much larger than the expansion time, which is typically about 10 to 20 Fermi. So this means that a mesonic gas, it can never stay in chemical equilibrium once it enters the chiral symmetry broken phase. Now, if the audience agrees with the results available in literature regarding the short equilibration time in chiral symmetric phase, then these arguments suggest that the chemical freeze out has to occur at the crossover temperature. Now, someone might question our conclusions saying that we haven't included baryons. So for that, I would say that the addition of baryons will not change the argument, because if we had included baryons, then the naturalness suggests that the slow mode relaxation time would change by the addition of this factor, where this sigma pi n is the pion nucleon cross section and nn denotes the equilibrium number density of nucleons. And at low energies, the pion nucleon cross section and pi pi cross section are roughly of the same order, whereas the densities it differ by 2 to 3 orders in magnitude as temperature is changed from 100 to 150 MeV, and therefore the effect of adding baryon will only be a few percent. However, for completeness, we are in the process of adding baryons in the calculations, but our current results and arguments strongly indicate that we understand the basic physics of chemical freeze out. And with this, I come to my conclusion slide. So firstly, we have constructed a kinetic theory of yields using pseudo-scalar mesons and unitarized cross sections from next to leading order chiral perturbation theory. The cross sections take care of the fact that pseudo-scalar mesons are pseudo-Goldstone bosons of chiral symmetry breaking. And in this first study, we have neglected baryons, but as I argued, we expect that addition of baryons should not affect our results and conclusions much. Now, the interactions are completely fixed by chiral symmetry, and the large values of relaxation times basically arises because of the low densities in the broken phase. At last, I discussed that a meson gas cannot attain chemical equilibrium, and the freeze out must occur at the chiral crossover temperature. So with this, I end the talk. Thank you.
Okay, thanks, Sushant. So we have time for questions. So please go ahead. I think anybody can ask questions now. Okay, Adipa asked the question. So in fact, you can unmute yourself and ask the question if you want, but I'll relay Adipa's question right now, which is, why is the singlet state eta prime of SU3 flavor symmetry group not included?
It's heavier, I think, right? So I said here that higher mass hadrons are neglected. I think eta prime has mass, if I correctly remember,
similar to the nucleon, I suppose.
Yeah. Yes, so it's heavier. So as I mentioned here, that since it is heavier, so we neglect baryons and higher mass hadrons.
Okay. Any other questions?
I have one question.
Okay, go ahead.
Sushant, yes. Why do you think that expansion will not affect your calculation?
Sorry, expansion?
I mean, dynamics of the medium dynamics.
No, so as I defined chemical freeze out in the very, I think, first slide, So you can see, so if the relaxation time is small, if you agree with this definition that if relaxation time is very small, then is small compared to expansion time scale, then chemical equilibrium will be maintained. But suppose relaxation time is very large compared to expansion time scale, then the system can never be in chemical equilibrium. So what I showed here, the calculations show that the relaxation time are very large. At the crossover temperature, it is about 100 Fermi, whereas the expansion time is about 20 Fermi, right? So which is much larger. So according to this, the freeze out.
Okay.
Did I answer your question?
Yes, yes.
Rishi, can I add something to that?
Yeah, go ahead. Yeah.
Sushant had a slide where he showed the linearized equation. If he can put that on. Yeah, right. So in this linearized equation, you have a d by dt on the left and these reaction terms on the right when you write it for a non-expanding fluid. If you have an expanding fluid, then you have an added term on the right-hand side, which is delta NA by tau x. Okay.
Yes, yes.
And you can see clearly from that it's a comparison of these two time scales which matters, tau x and the reaction time scale in a non-expanding fluid. That was the basis of his argument, which he showed right.
Yes. Yeah.
Thanks.
Adding one more thing, if you take care of expansion, it will be further basically.
Yeah, it will increase more.
Yeah, it will increase more.
Yeah, because that will pull you out of equilibrium.
Yeah.
Okay.
So I have a question. Yeah, Sushant. So if we include more resonances into this system, say like even in a typical HRG, you have like up to 2 GeV, like 200, 300 particles or resonances. So one argument is, of course, the mass is small, the effect can be small, but the other argument is they are in a very large in number, like an exponential, the spectrum. So do you think then it can have larger cross section, and can it affect this estimate?
So my answer would be, so can you see this slide? So what I mentioned here, that the resonances should not be included as explicit degrees of freedom. They have to be generated from the interactions with the from the interactions of the like pions, kaons. The lower mass hadrons, right? So so we do not need to include those degrees of freedom. They have to be dynamically generated from the interactions, but the results from chiral perturbation theory are available only till 1.2 GeV. So if the theory improves and if they should automatically generate the resonances, and yeah, we do not need to include them as explicit degrees of freedom.
Yeah, but even in this way, like through resonance, if you had a Lagrangian which took care of those resonances through interaction, then or is there some physical reason why we can argue that those cross sections may not be large or something? So you're saying in chiral perturbation theory, those resonances do not arise?
No, so in standard chiral perturbation theory, they do not arise. Yeah. So, but we have to enforce an extra unitarity condition to generate these resonances. So if I can show you one plot. Probably that will.
Can I, before you go to the plot, may I say something?
Yeah, go ahead.
So Sushant will show you how chiral perturbation theory generates them. Okay, but apart from that, the process that that Sandeep suggested has a problem. The resonance, and the problem is the following. Resonances are unstable objects, right? You don't want to put unstable objects into the Lagrangian. You would like to try to write the Lagrangian with things which are stable. Now, what is stable? We chose to take the things that are stable under strong interactions, the lightest things that are stable under strong interactions. Okay. Of course, there are other things which are stable under strong interactions. The nucleon is one of them, and we should add them in the future. And the idea would, if you were to put unstable particles, resonances into the Lagrangian directly, then you would have a problem of double counting, because the resonances would also arise through the process that Sushant will now tell you, but they're also there in the Lagrangian. Okay. So there is a problem when you take an interacting theory. There is a problem in doing what the Hadron Resonance Gas does. Hadron Resonance Gas actually works correctly only because everything is non-interacting. That's what I had to say, but Sushant can go on with this.
Yeah, I just wanted to show this plot. I mean, since you asked, so this blue band is the, I mean, I'll not go into the calculations, but this blue band shows the cross section from standard chiral perturbation theory if we do not unitarize it. So as you can see that at large energies, the cross section, so this is the cross section, sorry. So this is the cross section for isospin average pi pi to pi pi reaction. And as you can see that at large energies, the cross section will go to large values. But if we perform unitarization, so this has to be an extra condition, then you can see that it will generate a resonance at, I mean, the peak at the rho mass, like root S is equals to 770 MeV. And then since the theory is unitarized, this will go to 0 for large root S. So even though we have not generated higher resonance, but up to 1.2 GeV, which can be like, because the range of temperature which we are considering, this should be sufficient.
Okay, so so that if we are supposed to calculate the thermodynamics, say, like pressure or energy density with temperature, with this system, you can get this like P versus T or E versus T, these curves. So like in the non-interacting HRG, the amount of pressure and energy density that you generate, so with just this system, you will get that?
I think yes, because this will take, so this interaction, this cross sections will take care of the fact, I mean, will take care of the decay width and the lifetime, I mean, through this. So yes, if we have all the, I mean, so I mean, how should I explain? So suppose we had a theory which could generate all the resonances through, I mean, with the interactions of low-lying hadrons, then yes, your question should be, the answer should be yes. We should get that pressure and temperature, right?
Yeah. So this 1.2 GeV cutoff that you're saying beyond that, maybe this cross section is going.
Yeah, we are getting resonances only till 1.2 GeV. After that, I mean, the chiral perturbation theory either has to be, I mean, we have to go to like next to leading order, and
okay, so it is in those. Okay, okay. Thank you. Thank you, sir.
Sushant, maybe you should say a little bit more about that, because this is not a guess. Why you need next to leading order beyond 1.2 GeV or so. This is not a guess, right? You know the answer, so you should say it.
Sorry, sir, I didn't get your point. Sorry.
Okay, maybe I'll answer that since you have temporarily forgotten. But it turns out that if I, for technical reasons which Sushant can explain, probably he has a backup slide. It turns out that if you take the NLO matrix elements and unitarize using NLO, then you can generate only the spin 0 and spin 1 resonances. And one can check that in order to generate the resonances of spin 2, you need to go to next to leading order in chiral perturbation theory. That's why he mentioned that 1 point.
Okay. Thanks.
So actually, maybe there are no further questions. So I'll ask one. So can you explain briefly what unitarization, how it works, in the sense that, so we know that chiral effective theory is a good theory below, let's say, 1.2 GeV or so, but you want the behavior a little at larger energies so that it's unitary. So maybe you can say a few words how that works.
Yes.
Yeah.
So
Okay, go ahead.
I would say that this chiral perturbation theory is valid. Below the till 500 MeV, not till 1.2 GeV.
Sure.
So
Okay.
we perform this unitarization. So this method is inverse amplitude method, as I am showing in this on the slide. So this has a rigorous derivation through dispersion relations, but I'll just give the prescription here. So this S matrix, basically it is written in terms of this T matrix like this, where the sigma is 2 over square root first, and this is the center of mass momentum. And unitarity demands that SS dagger is 1. So equivalently, with this turns out that this T matrix has to satisfy this condition, that imaginary part of T inverse has to be minus sigma. Now, for a perturbative theory, I can write this the amplitude as like this will be tree level. This will be the first loop, and one loop, two loops, and so on. So then the prescription is that the unitarized amplitude will be given by this expression, where T0 is the dimension of the T matrix. It's a matrix. So let us say if I am below the kk bar threshold, then I have only one state. Like for example, suppose I'm considering rho channel. So below the kk bar threshold, I have only one state, which is pi pi. So this will be just a number. However, above the threshold, I have two coupled states, that is pi pi and kk bar. So this will be a 2 by 2 matrix. So that is why I've written it in a matrix notation. So the prescription is that the unitarized amplitude, if we know the perturbative expansion in the theory, then the unitarized amplitude will be given by this, provided the perturbative amplitude satisfy this condition, right? And it so happens that in chiral perturbation theory, the tree level and the one loop amplitudes, they do satisfy this conditions, and hence we can perform this unitarization. And here I have done as a check, you can see that if this TU is the unitarized amplitude, then I can find the imaginary part of the inverse of TU, and this turns out to be minus sigma, consistent with the unitarity condition. So with this, it can be, the validity of the theory can be expanded till like not 500 MeV, but till 1.2 GeV.
Okay, thanks. So there was one more question that more a discussion question rather than a question. Rajiv asked this, but I think he's left. But he was curious about what is the width of the lattice band in MEV, and is it smaller in recent results? If you go to your slides, if somebody knows, they can comment
I
on this.
cannot comment on this. I am probably Shorindu sir.
Sorry, what was the question? Sorry, I didn't understand.
The question was, what is the width of the lattice band in MEV, and is it smaller in recent results?
Oh, I see. Well, yeah, this is what Andronich et al. Quote.
Okay.
And, this agreement can only be an approximate agreement, right? TCU.
Yeah.
Because the lattice, I mean, the position of the crossover itself is an undefined quantity. And when Lattice measures it, they give one definition, one particular definition, and then they ask for the error band in statistical error estimate using that definition. Okay, and that can of course decrease as your statistics improves. Okay, but a crossover means that there could be multiple definitions of where is the crossover, and they don't have to agree.
Yeah, that's right.
Okay, and so that actually means that the position of the crossover is in some sense indefinite. When does chiral symmetry get restored? That question is a little vague. At what temperature does chiral symmetry get restored, or at what temperature does chiral symmetry get broken? These are slightly vague questions. I think that's the answer that's the best answer I can give. If somebody else has a more interesting answer, it would be nice to hear.
Maybe one thought that occurs to me is even the freeze-out temperature also is a little bit smoothish in the following sense that you only give a condition that it should be greater than the crossover temperature from the results, because that's the point where the tau is very large compared to the expansion. So you can say that it should be a little bit before, and so there is a little bit of an uncertainty in that direction also.
Sorry, I didn't
Can I
understand.
interpret things for the freeze out also that way? So you have the statement that tau at crossover is significantly larger than the expansion rate.
Right.
Right. So tau was about 100 Fermi, while the expansion rate was about 10, 20 Fermi. So already you could say you could have it a little bit higher. The temperature could be a little bit higher, but of course at that point the theory starts breaking down also. So there's an uncertainty in the positive direction for the temperature in the freeze out calculation also, right?
Yes, I think that's yes.
Yeah. Okay, so if there are no further questions, then let's thank the speaker once. Oh, Sandeep has a question.
Yeah. Okay. So the other way, there is this estimate of chemical freeze-out temperature also through these higher moments, right? And that is coming a little lower, right? But so there is the argument then that there is some scattering. So from the yield, we are getting this chemical freeze-out to temperature to be close to crossover. But the other way to define is through the these higher moments. And there it's about 10-15 MeV, usually lower.
I think if one of my collaborators on that issue is here, I don't know. I haven't looked at the list of participants.
No, Nu is not here. Yeah.
And Devashish is also not here. Devashish Malik is not here.
No.
Well, we don't find something lower. Okay, we don't see that it is 10 to 15 MeV lower.
Okay.
Number one, but of course, when you say higher moments, it turns out that first moment, that is the second moment, and third moments can possibly be described, but the fourth moment cannot be described in the Hadron Resonance Gas. So there is a question about why moments stop working. And our argument, at least in the version that we put out on the archive last year, our argument is that this has to do the same thing, that there is that freeze-out is a dynamical process, and that the lower moments see something close to the peak of a thermal distribution, whereas higher moments observe the tail, and tails take longer to thermalize than peaks.
Okay. So, but naively, I mean, this estimate seems to suggest that as soon as this chiral crossover will happen, everything will go completely, I mean, out of equilibrium, right? So, can we still think now chemical freeze out like a dynamical, like spread out?
Yeah, because we don't know whether it goes out of equilibrium already in before it comes to the chiral crossover.
Okay. Uh-huh. Okay.
Especially if it passes close to a critical point.
Right. Okay. Yeah. Okay. Thank you.